Time to start. Oh, by the way, my name is Pan. Today the topic is argumentations and sheaves, and the first speaker is Duan Xia, and he's good. He's okay for short for Duan.
Yeah,
Alright.
okay, probably.
Cool. And he's going to talk about Legendre knots and constructible sheaves.
Yeah, thank you. Okay, then let's start. So my outline is maybe I should talk about what will I do, right? The philosophy. And maybe it should be here. So given Legendrian in R3, or it could be also in S1 cross R2, or it could be actually anywhere. So I should keep writing it. All manifolds I know. No. So given Legendrian like this in our example, so we see it in a cotangent bundle. Actually, not cotangent bundle. We see it in a T infinity. M, let's say. So let's call this M.
Maybe we should change
Yeah,
the
sorry.
No. Throw it away. There's a trash can. The
Sorry?
one that doesn't work, you can throw it in the trash.
So yeah, system here. Sorry.
I
didn't want to miss that. Hey, you are throwing this?
Yes, yeah.
We are a lot of better. So, okay, we see it in a kind of in a subset of this sphere bundle, you know. Anyway, so then we associate a Lagrangian taking common, and for this Lagrangian, we will consider the sheaves on the base. So this is not M, therefore this is R2. So we will consider sheaf on the base, whose micro support is on this Lagrangian that we construct, but whatever this means. So I will describe this kind of thing. So we will just calculate the sheaves that they will give us a category of sheaves, and which is associated with Lagrangian. Then we will say that this is invariant of this Lagrangian, and therefore it's Legendrian. And this category has some description in terms of Fukaya category, and the combinatorial description, which is really important so that we can calculate it. So, yeah, let's start to construct this thing. Right? So let's start with sheaves. So maybe I should give the definition of sheaf real quick. So sheaf is a function from open set category, which means objects are open set and morphisms are inclusions of open sets, and actually it's covariant factor to a category. So let's say which category, like for us, let's say it's category of K modules, and K here is, let's say, commutative ring, but I will take it as a field. So this is called actually pre-sheaf, and it also satisfies Goulding property, which is can be written like this. I should write the general version of it. So if I have U, open cover UIs, and then UIs have intersection UIJ, then I should take the limit of this diagram. And it should give you U. So basically this says that shift just gives K modules to each open set, and so if you want to understand the union of this open set, big set, then you just glue the small part. So if you know local part and if you know the restriction at the intersection, you just take their gluing. So you just glue them and get the whole thing. So this is, so which means this local part determines like global part. So therefore we can calculate it locally and find the global thing, which therefore sheaves are important. And so what else? So for example, so we have like a constant shape, right? let's say R space is M, then constant shifts on M. Let's say K is a K module. Constant shift just gives K on connected component. Always give K. Okay. And let's talk about quick stalk. Stalk is, so on your M there's a point X, and you look its neighborhood open sets, and you calculate your shift there, and you zoom there. Then you get and then again a K module, which is your stalk. So stalk of X is limit through this open set containing X, and this is stalk. And for our purpose, I will tell that locally constant shift is a shift which is locally constant. But that is a real trivial definition. So I should say, if the stalks are always the same, then I will call it locally constant shift. So let's say constant stalk, isomorphic stalk, locally constant shift. Okay, this is kind of basic definition. Now you should move on the I should move on. So other definition. For example, for us now, like, okay, this is the classic theory of shifts, but now we will deal with constructible shifts, which have combinatorial nature, really good nature. So, but for that we need to understand so witness stratification. I won't talk about this, but just like you divide your manifold or topological space to pieces. It doesn't need to be manifold. Yes. So pieces of these are connected manifolds, which you call strata. So if they have dimension 0, for example, we call it zero dimension stratum, etc. So for example, you can R2 you can divide it like this. Let's say this is stratification of R2, which is we have point and we have one dimension strata, we have two dimension strata, and they satisfy some properties which they will always satisfy your mind also. I won't talk about them, but they are really reasonable. There is no too much stuff here. They are locally kind of finite, everything. Okay. So then I define constructible shift. With respect to, so let's say this kind of stuff, which is my S, is certification. Okay. So it is like S contains stratas like this. SI. So this is stratification. So then constructible shift with respect to this S is. So if my shift is locally constant on each, so I have shift and this is locally constant on each of this strata, it's locally constant. Then I call it constructible with respect to this strata. So
And when you say locally constant here, since those stratas are not open, so do you mean
yeah, you can. So this is not like I'm not calculating my shift there. I am restricting my shift there with push forward. You can think like this. So I can restrict my shift to. It doesn't need to be open set. I can restrict other sets also. So I'm just restricting my shift there. I ask it to be locally constant. Or the easy way to think about this, using my other characterization of locally constant shift. So its stalks are the same, right? Constant stalk and locally constant shift. So you can say on stratum, it has to look constant stone instead of this. If it's constant stone. This is also kind of valid definition. So. So why is this definition important? Because it makes your shifts really easy. So because for example here, your shift is same here, same here, same here, and same in this region, right? Only changes where the stratum changes. So your shift changes where this kind of place, and this kind of place have a combinatorial nature because of this definition of stratification. It has finite nature, kind of. So you just understand this kind of points and you understand your shift. But we will talk about more on this in the combinatorial part, but that's it. So constructible shifts in this case is if there exists this kind of stratification that makes your shift constructible, then it's a constructible shift. Okay. Now I can define my crazy theory category. So category of shifts which are constructible. So my space is M, and this is category, and its objects are. So now we are doing substitution. So we take chain complexes of. It is chain complexes of constructible shifts with some additional things which chronologically bounded and etc. And morphisms are morphism between chain complexes, but they don't need to be chainless. They can have any degree K morphisms between chain complexes. So, okay. So this makes this is actually chain complex because our morphisms are chain complex and it has differential on morphism, which is called, this is DG category, but actually I won't stay on this too much. So okay, so far good.
It's good,
It's like
but it's becoming harder to read again. So
Ah,
I don't know if you need to push harder or make it angle the marker or
Let me-
just one or something.
I think you one then, yeah.
Either one, yeah. Just switch markers.
Maybe I should not throw away before trying this.
It's okay.
This is not that good also.
Try the other black. I mean, I don't know.
The
Just
blue
keep
one might
trying.
be unerasable. Is it?
No, that's a different
There's a
type
different one. Okay.
So this is okay?
Yeah.
that's good.
for now.
This I use, but I can throw it. I don't throw even if I use one single thing. Okay, this category is like this object is chain complex, so focus on objects maybe. So, and we divide by acyclics actually. So this is naive version of it. It's naive. We divide by acyclics. Acyclics means just chain complex, it gives zero homology, then homology, then we count it as a zero. But don't worry about this for now. And therefore it has a derived category. Actually we will mostly be interested in derived category of it. In derived category we have chain complexes and the morphisms are not like the decay morphism, just chain morphism, how it's called? Chain map, which are, so we just assume this, like if a map gives isomorphism in a homology, then we call it isomorphism, which is the definition of quasi-isomorphism.
Morphisms in the sheaf category are not necessarily chain maps.
I'm sorry?
Morphisms in the sheaf category are not necessarily chain maps.
Since morphisms are chain complexes of more, actually, this is a chain gives us a chain complex.
But they're not chain maps.
This is not chain maps. So I take its derived category, then it becomes chain maps with some identification. But here we are really free, so that's the actual power of this theorem. You are here, you are free. You have all homotopies. Huh? You can-
So maybe you shouldn't say degree K morphism because you're defining morphism.
No, but in the chain.
Like degree K linear maps.
Are you sure? I can say.
Alright.
So, is that alright?
And then there's differential maybe on this classified.
Yeah, there's a differential. Because I don't want to focus on this because this part is I want to even forget it. Okay, now singular support. Now maybe some of you don't know this thing, but singular support or micro support. So this thing is so for sheaf you have concept support, which your stocks are not the place that your stocks are non-zero is support of your sheaf. This place is in M and closure of this. Closure of this thing is support. Now we will define micro support, which has more information about your shift. So micro support is philosophy like this. Micro support measures calculate the change in your shift. So because if your shift is always constant, then for example, your micro support is kind of trivial. But if there's a change in your shift, at some point it changes. Then this captures this kind of thing, this micro support, and which is called SS. I want to keep this thing. So how can we define this? Single support. We will measure the places where changes happen, and you will do like this. So first of all, this lives in the T star M, okay? Because it also records direction of change. So point where your shift change and the direction. So this lives here. And so how can you see that a point belongs here or not? So you take this point X, okay? You take your point, and you take a really small neighborhood of this X, and you see this direction. Maybe you can use function for it, right? So let's define a function which is 0 at X, and its differential at X is P. So let's say F, a nice function. So F is already a nice function. So in terms of F, this part is positive, this part is negative, right? This is F equals 0 part, this is F greater than 0, F smaller than 0. So what we want to do is, we want to measure the change. Oh, thank you very much.
These will work.
Not for that? I couldn't do it. I thought it's high tech. I don't know. Okay. So what I want to do is I want to understand behavior of my shift after passing this point. Like I compare this region before passing the point with the other color region. I should choose the right one. So I compare this, my shift on this open set and this open set, comparing like this and this, and compare if they are the same or not. That's so. That will tell me about if this point is, let's say, bad point or not. What is bad point? Bad point. If it's here, it's bad point, let's say. Or maybe we should call good point, I don't know. Important points. Sorry, important point. Okay, so how can you do this formula? So the thing is, now we are in this kind of setting. The thing is, so we should not just see sections. Sections means this open set. The thing sheaf associated open set. We should think drive sections, you know. So which is annoying, but like derived version of sections, which you can somehow, if you have a shift, you can find the derived sections also, if you know your shift. I will tell about this part, what the definition was. So, what you compare again? You compare, let's say this is f delta and f minus delta, and I compare my shift. So this is taking section. This is same as. So if I write this is same as fu. Okay. This is good. So we will. This is section. Taking section. This is functor. We will take derived version of this functor, which is rf, and rf intersection. I compare this one with smaller one. Okay. And since this contains this, there's a restriction map, right? This is restriction map. And if this restriction map, if it is not quasi-isomorphism, that means that there's a change, right? Then xp is inside your singular support.
You forgot the sheaf in your formula. Sheaf F.
Yeah, sorry.
Okay.
Yeah, what are we calculating? Yeah, this is sections of the shift, and if it's not isomorphic, then this gives this. So, and singular support is defined like this kind of points, important points, like chloride again. Okay.
So how do you know what function little f to use?
Oh, yeah, you can choose
You choose-
a nice function. What is nice function? No, just like any function, I believe this there's a result. You can choose any function. It is invariant.
Force division like small epsilon or something?
Yeah, it should be actually. You should look this limit,
Yeah.
but at some point we think like this stabilized. So it's if it's small neighborhood, then everything's stabilized. There you can look your shift. Like maybe in like crazy setting or situation, maybe you need to take limit. So, but for my case, I'm working with constructive shift. So for us, no problem. If this definition is not working in general.
And what did the R part mean? You said something about derived.
And so yeah, R is derived. So for every factor, you can find the derived version of it, which is maybe I don't want to talk about. But you have chain complexes. You have chain complex. You add your functor there, but it's not a good theory because you need to first resolve your chain complex by injectives. Then you apply your functor. And if it's like complex, you actually get double complex. Then you make it total complex. Then you apply your functor, which you get is this thing. So there is a procedure, which means it's not magic.
But I guess in this case, you simply say that if you have the original sheet, you cannot just look at that. You have to take this injected resolution and let him do that from injected resolution. That's
Injected resolution of my shift, you mean?
yeah, exactly.
Yeah.
So this R means into that. Consider injected resolution and
Yeah.
the homology. That's the.
Yeah. Yeah, like if I constant shift, for example, constant shift is really simple, right? But if I want to understand this drive section, I need to resolve constant shift. And you can resolve it by singular chains or DRAM or whatever. They are all acyclic resolution. Or then you can apply that and you get your answer. But I will give an answer which, for example, constant shift. So remember our constant shift, which gives us always same thing. But now I will. What are these derived sections, for example? Derived sections. So constant shift. What are they? So they are just chain. What do you, single chain or few? Which is quasi-isomorphic to homotopy also. Okay. For if it's like analogous, if I calculate my shift there on analogous, it will give me the k and k. K. It will give this on analogous. This is this region. It will give this. So which means one can glue these pieces to get homology of everything, in particular, because it measures, it is a shift which gives homology, so you can glue whatever you want to get homology of that set. So maybe I should hurry up. Maybe some example before I pass on to the real stuff. So some examples with singular support. For example, what is the singular support of constant shift? You think it is zero section. So I should tell this property also. Property of singular support is if I intersect with zero section. Okay, X and M are the same thing in my talk, okay? So, then it gives your support. So you don't need to think about zero, P equals zero. You don't need to think about this case. Because it gives zero support of your shift. Just, you only care about directions. So here, there's no change, right? It's constant shift, so there's no change in any direction, so you should give only the support. And also, there's this property of single support is single support is local, which means you calculate locally, right? Like you only care about local part of it. So this implies that locally constant shifts also has this property. Let's say locally constant shifts has L of X also has this property because locally it's local shift, constant shift. So it will give the same answer with the constant shift. And we have single support is conical because we care about only direction, right? How far is direction? Is just direction. And you take R multiplied by R. You take all of these things to.
Alex in this previous line, is that just any locally constant shift?
Yeah. Sorry, I should write this. Locally constant shift on X. And so this can be also singular subset of T star M because it can have, we will see, it can be singular. And but there's a nice result of Kashura-Shapiro, I believe, which is, I believe, again, deep result. It says this thing. I think this is kind of really important thing about the singular support. This thing is isotropic subset of T star M. Co-isotropic, sorry. Is that so? Co-isotropic, I said, I'm sorry. Okay. But there are more of that which justify why we work with constructible shifts. So if F is constructible, right? then this singular support is actually Lagrangian. We have this result.
Lagrangian submate.
Of it's a Lagrangian variant.
Subset.
Of T square. But it can be singular, right? It's not.
Yeah.
Let's say singular Lagrangian, then of T star M.
I'm a little confused because if it has to be coisotropic and isotropic, if it has singularities as a Whitney stratified subset, I would think that the strata of lower dimension would just be isotropic but not coisotropic. I mean, a Lagrangian Whitney stratified subset has some lower dimensional strata which are isotropic.
Oh, you don't really care about that. You're just caring about like how things are coming into that lower strata. So at that point, you're sort of looking at all the directions that things can come in.
The singular support is
Instead, so
coisotropic in the contingent point
Yeah.
of the strata.
It's more like the span of those directions than
It's more like the conormal of the stratification.
Yeah.
It's more like the stratification itself.
Is it problem regarding definition of singular support? If it's like that, I will give some examples so maybe you grasp this concept
Yeah,
better.
examples would be great.
Yeah. Okay. So we also have some other properties, but for now anyway, but we should do a good at. Okay, my remark is this. So constructive shifts, Lagrangian. So we want to work with constructible shifts. That kind of justifies this. So one example is, let's take M, and let's take a closed set of it. So we define constant shifts on Z. Okay, let's say K is a field or something. Constant of shifts on Z defined as actually push forward or something. I will skip this part, so I will just say it's usual. Let's just care about the right sections, okay? It gives homology where the part that it intersects. Same thing with constant shift, but just supported here on this thing. Okay. So let's find the single support of this problem, for example. So what should we do? First, let's see inside. Inside is log constant shift, right? There's no change inside, because if I choose U here, it becomes Z disappears and this is constant shift. So inside there is no direction. So then we should have. Also, I should maybe assume this Z has smooth boundary. No, Z has smooth. Then this Z has straight. Okay, boundary smooth. So inside this is 0. Z interior. What else boundary? I never care about 0 part, right? Just first write this. So it is part that stays in 0 is just Z. This is the place where it's supported. So let's just care about directions now. So inside there's no direction. That gives us a singular support. Outside, similar, right? Outside is a 0 shift. No direction. But what about boundary? And this should stay. on boundary. So let's zoom to boundary. See, it's a smooth track, so it will become like this. So I choose a point on boundary X and a direction. Which direction line? I said. If let's see if this point direction is in singular support. So we expect there's some change, right? But we don't know which direction. So okay, I choose X and P. So what should I do? I take a neighborhood of it. And what I compare? I compare before and after, let's say. Before and after. What is before? This part, right? This is before. And what is after? After this whole thing. I don't need to. So, I compare this with the whole thing. Why whole thing? I should choose maybe actually here, but it doesn't change. So, whole thing versus this thing. So, on whole thing, what is this? Since this is contractible, it will give whole. Let's say this thing as A, and this small thing B. So, what is on my? From now on, when I say this, this is drive section, okay? FA, drive section. So, what is FA? This is. Remember, the definition is intersection with Z. So it measures here actually. It is contractible, it is K. Just K. It's homogeneous K. Here. What is B? It is this place. And my shift gives homology of that place, that's also K. And what is the restriction? That restricts this, but it's constant shift there. It's identity. So this is quasi-dimorphism. We don't have this direction. Good point. Nice point. No change. No change. What about the other direction? We should check all direction, but just illustration. What about this direction? So I should compare this before part with whole thing again. Okay? Now let's call this as B, A, B. What is now FA? I mixed up some stuff here. No? Okay, sorry. So FA is same thing, right? K. What is FB? FB is in 0 part, so 0. So this restriction is 0, so it is not quasi-isomorphism. Not quasi-isomorphism. So this point is in a singular support. So which means that, and there are no other one, I claim. You can check as an exercise, but which means that for this kind of objects, for shears, the singular support is inward direction. So, yes, equals 0 section of Z plus on boundary inward directions. On boundary of Z. Does that make sense? So inward means so you should take all directions. It's actually fiber. So you get a what? You get this.
Is
Not
it
this.
any inward?
So
No.
no. Like
So if you draw skew,
orthogonal. Let's say.
But I mean,
But what's orthogonal? It's
Yeah.
smooth, so orthogonal.
you can draw the skew picture, right? Like,
So
the red set is kind of skewed, and
So-
it also doesn't change.
So see here. So I will do it quickly. So see this direction. So you compare this one with whole thing, but whatever you draw, it will always intersect this place. Only the thing that won't intersect this. If you choose your delta small, everything. So if you choose good. Okay? This becomes a shift talk actually, like I should tell something about legendaries probably. But let me give you this last example, which is open. What if it's open? I won't calculate it. But this open U, let's say, not U, V, let's say, or Y. Y. And my shift, constant shift on Y defined as its stokes inside are K, but on boundary its stokes are not K, like it's support on this. But now it's that the drive section actually I don't know. I don't know its derived section. Because the other ones, derived sections can be calculated by push forwards of something, but here, it's, at least I don't know, but I have some property which relates this. If you have, let's say, open, hole, and close part, it doesn't need to be constant shift, but this, for example, this is U, this is Z, this is Y, this is Z, this is X, let's say. And so that Y union Z is X, and the intersection is empty. If you have this kind of exact sequence or distinguished triangle or anything, then you have this property, which I use to calculate this. I use this to calculate everything actually. I know some basic example of that. So did you get what I mean? I means you can put open instead of I, wall, or doesn't matter the order. So unless you have this, all of, you can put any of them to anywhere there. So Ki is bounded by this and this. And this is symmetric difference, which we ignore intersection. So using this, for this we can find, you can think about it, but this is actually zero section of Y union outward vectors this time. You can think about this. Okay. Now I can define my final category in the end. So remember, we defined the shift category. Now we focus on its subcategory, full subcategory, which is denoted by this. This lambda means this subcategory of this shift category. But now our shifts inside this are their microsupport, such that their microsupport lives inside lambda. So we are dealing with constructible shifts whose microsupport stays in lambda. So a question?
Lambda is on the boundary, right? So, or is
So-
lambda Lagrangian or
So
what?
yeah, there's this confusion now. Sorry, I should say L maybe to make it. Let's say L is a conic Lagrangian. Conic Lagrangian means it's on R action of fibers is invariant. R positive action. Sorry. So if your single support lives inside L, you have this category. And maybe I should talk about invariance quickly because I won't have time. Then there is a result of Guillermo-Kashimura-Shafiras. We said that this is invariant under Hamiltonian isotopy of L, kind of. Actually, this is like conclusion of this. Oh yeah. Okay, so that's nice. We get the invariant for free. And then, what if I have Legendre? Then, sorry.
Sorry, I think they really mean that you remove the zero section of both the singular support and the Lagrangian.
I'm sorry.
I think the result says you actually remove the zero section from your singular support and the Lagrangian.
You mean this result?
Yes.
This result is not this. I should say this. So in the end, we get this. Let's say. Yeah, I don't want to talk about this because I even don't understand quite well.
You mean lambda there instead of L? Would that fix it?
Huh?
What?
If it was lambda instead of L, would that be more?
Yes, I think that's what it said. Or you can, or I think the equivalent you should put like L, it contains the entire zero section.
Yeah.
Otherwise, like if L doesn't contain the entire section, zero section, and
You
then
may be
add
right, yeah.
the local system, and then
Yeah, but he said that he's going to ignore the section.
He said that he ignored zero section.
You said that?
Yeah, he said that. He
Sorry.
said, oh, we don't care about it.
So let me do like this. Maybe I should go the wrong direction. First, start with Legendarian and say this result. Well, for example, you start with Legendarian, okay? Since we care about Legendaries here. So you can construct Lagrangian, right? Just taking cone and putting the zero section. So R lambda union zero section of M. This is Lagrangian, like, do you agree? Okay.
So, sorry to slow you down, but
No.
maybe
No, no.
you should remind people what T infinity M is, which is where these Legendarians are sitting.
Sure, yeah. I will tell it just after this. Well, I can. So this thing lives. No, I should tell it here, of course. That's obvious, right? Yeah, I'm sorry. Yeah, this lives in the. What do you call this?
We call it S star.
Kostifer bundle.
Yeah.
Okay, sorry. So Kostifer bundle, lambda lives in Kostifer bundle, and you take this cone, and you take union, then you get a Lagrangian. This Lagrangian is satisfies what you ask, then it is invariant. But we said that by definition we define it like this. This, okay? When I say Lagrangian, actually I mean this Lagrangian, which is like this. So this is invariant of Lagrangian isotopy then, right? So maybe.
So sorry, in particularly all locally constant sheets are invariant, right?
Yeah, exactly. We have all local constant sheaves because they are living in this. At least we have this. For example, if I take zero section as my Lagrangian in T star M, then you get local systems. Oh, yeah. Okay. So now maybe this part is over. This part is over. See, I am in a half of my talk. Just one clever move. So, now Foucault, I will just talk about this a bit. Foucault theoretical description. This is from Nadler and Zaslow. Nadler and Zaslow. So, we define this category for M, right? Forget about lambda right now. And there is this category which is defined for T star M, which is symmetric manifold. It has kind of category, but it's defined in, it's not compact anything. So it's defined in this paper. So like its Lagrangians are exact Lagrangians, which has nice boundary in the infinity. With M nice and maybe you know Foucault category, but just I will explain objects for now. Objects are this Lagrangians here, and we have sheaves here, so they correspond to each other. So there is this result. This is quasi-equivalence. So let's say quasi-equivalence, which is in this setting, which means they are same thing, kind of. And how you do this? Idea is simple. That the Kashwara-Shapiro result, right? The idea, starting idea is, remember, this is constructible sheaves, by the way. I don't put C in my talk, but so if you have sheaf here, then you can take a singular support, right? Which is Lagrangian because it's constructible. So I put. No, this is singular. This is singular, so you should perturb with a function. Of course, there are many stuff to do. Actually, you can take all F actually like. What you should do, you see this subcategory, sub-digit category, which is consists of simple sheaves, which generates this sheaf category that you consider that embeds inside this, which is something that embeds into this. But the idea is this, so starting idea is this one. So for example, if you have the closed interval, let's say, what you get? You get invert vectors, right? So we are in R. Our shift is here, close. Let's say this is closed set, this is KZ. Then what are the single support? What is the single support? this inward direction and boundary, and inside this is just thing. So if I draw in T star, what do I draw? I will draw 0 section, and here which direction? Inward. Inward, let's say inward means right means up. Let's say right means up, and here it is left. Left means down. So it will give this thing, which is singular Lagrange, and then they disturb perturb this thing to make it smooth, and it lives here. That's the idea. Okay. One more check. Now, last part, combinatorial description.
Sorry.
Probably many things is wrong, but here, you know what I said.
Is anybody else going to discuss the Fukai category? It's the first time it appeared, and it feels to me that morphism is quite essential.
We'll do it.
So
You want?
we're not going to use it today.
Maybe Ying will use. Where is he?
Fukai, okay, great.
You will.
Yeah, I will say a little bit about that.
He will talk about. So you want more information about this Fukai?
But I'm also confusing with this thing, because I mean your singular Lagrangian, you need to do Lagrange surgery to define like form spaces, right?
Yeah, but let's actually like the most important part in my talk is this. But if someone will introduce this thing, then he can give maybe. But I should say this infinitesimal version of
Yes,
this.
it is good to observe that it's the infinitesimal version. So I think tomorrow we're going to be dealing with a different version.
There is also wrap version of this, and there are wrap sheaves also. There are this part of this. If you are asking about this, but for me I should say infinite unwrapped version of unwrapped Fukai categories. Okay. Now combinatorial description. Because I'm more interested in combinatorics, then I can calculate. So let me see where I am. So remember, constructive shifts has some combinatorial nature, then it's not strange that they have some combinatorial nature, like we can assign something combinatorial to them. So, for example, first I will define this definition. So, given a stratification, I can define a category associated with this, a representation of this, let's say. So, so if, for example, you have this is my favorite knot, which is a knot. So this, maybe I should have some crossing, right? Then I get all different. So first of all, the natural way to stratify this is this. And so maybe I should, before talk about what does this mean, right? So I am really quickly, I didn't talk about in the beginning. So you are given legend in R3. So what we do is, we are embedding this in T star T infinity minus R2. What does this mean? So, what is T star R2? This has these two coordinates XZ and the fiber coordinates, right? PX, PZ. But this is, since this is infinity, we take this R action. So this is Economist class. So minus means that you take this as minus. So you only care about downward. So this is subset of this infinity R2. You only care about downward directions. And I claim that R3 can be embedded on this. I mean, they are the contact isomorphic actually. By this. So if you x, y, z, you just send it x, z, and y minus 1. So which means that y corresponds to this direction, px. So if I have not in R, if I draw something in R3, you should see that x and z are this one, and y corresponds to this direction, and what? So, and we know we know this property, right? So, my picture, so I will use this front projection, right? This is front projection because I have something here like this. It gives me XZ coordinate. So my pictures will live in XZ, and you should deduce what is Y.
So again, M is R2.
Yeah, and now, from now on, the theories start to become for R2. Like, it's not that general, let's say. Maybe at some point it will be general, but I will mention that point. So here it is M is R2. Does it make sense to say R2? Okay. Not is in R3. Sure. So okay. If I draw this picture, so how can we deduce the Lagrangian associated to this? Let's think about this. So the Lagrangian has zero section this, right? So this is front projection of my Lagrangian. It's not this like. This is the place where fibers are, right? This place. I have whole zero section. But in which direction I have these fibers? I need to understand this, looking to front direction. So remember, it gives, Y is this, right? But what I use is, I take this direction, Y minus 1. What is Y minus 1? This is actually 1Y or something like that. Like somehow, really basic mathematics, you should get this direction for Y minus 1. Am I right? Yeah, so this direction corresponds to the perpendicular direction which is downward. So which means that for your math, when you see this picture, you imagine this fibers. You just take downward vectors which is perpendicular to your thing, and here on cos is downward, like this. On crossing it is in this direction. It's two direction. On crossing you have not single fiber, two fiber. Yeah. Two. Okay. So we need to calculate the things on this. By the way, my talk is I think 15 minutes. I have 15 minutes for, right? Or less. Maybe it's too much to focus on that. I'm sorry. So, okay, I need to be quick. So, now I define this category. So, given certification of my space, and there's a natural way to give a certification for these pictures. How? You just take points as a zero-dimensional strata, this art as one-dimensional strata, and the region as a two-dimensional strata. Here, this natural certification. Okay. So, and we always use this certification as a starting point, then you define this category of, let's define this, not representations yet, but objects are strata, and morphisms are so. What does this mean? So, for example, and we define star of some strata, which is actually to think that satisfies this, like list of J, such that so what does this mean? So this means this. So if you have, for example, unknot. How is my category? So I have points here. Okay, this is our object, that's strata. 1 point here, 1 point here, 1 point here, 1 point here. Inside is the strata, and outside is strata, right? So what are my morphisms? My morphisms are going from this. So these arcs contain this So you just look the neighborhood of your strata, and if it intersects, you get it. Okay, just small neighborhood. So the things that intersect with this are everything, kind of. Not everything, but this, and outside, and this. So at this point, it's the same. We have this picture. What about this arcs? When you take neighborhood of arc, it intersects these two regions. So there's a map through this region. Okay. Does it make sense? You just look exit paths, kind of. Not exit paths, I should not say this, but you just try to quit from go to higher dimension strata. And there is representations of this, which is functor category, with K-mod, which is you put chain complex to each of these objects and chain morphism to each arrows. Does it make sense? There's representations of the just put V, W, and the arrows. Our aim is describing our shift category with this kind of diagrams.
Are these your complexes of these, or just?
Yeah, it's complexes because they will correspond to neighborhood of your shift, and your shift gives chain complexes or opposites, right?
Yeah.
So they will actually be chain complexes. So actually K-mod is here, is a DG category of K-mod, K-modules. And if you see the derived version is like we usually work derived sense, but DG category, let's say. So there is this proposition which shows the combinatorial nature of the thing. So
Does it say fun? That's set for fun?
this is fun, yeah. Functor category of from cell to K-mod. K-mod means
So then you should add some kind of finiteness condition somewhere.
Hmm?
You should add some finiteness condition somewhere.
for what? For this?
Modules. It should be perfect module.
Yeah, we actually always do this. We ask is cohomology bounded, etc. You mean this kind of conditions? Yeah, our category has this kind of conditions already inside, but I don't mention that much. But as is also finite thing. So my front projection is finite for this. Everything should be like this kind of diagrams. So okay, my claim is that from constructible shapes, from which are constructible, which is back to this S, they're dysfunctional, let me say. Shifts of K module which are constructible with respect to this, and there's this functor. We have this functor. How can you construct this functor? For example, if you define shift here, what you do? You will give opposites to everywhere, right? I will give opposites here, 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 here. But if I give opposites here, so why should I give an opposite here also? Because they will be saying this is local constant, right? That can be monodromy, but that can be ignored that this is isomorphism if S is regular cell complex, which means that all strata and all stars are contractible. So on your shape, if everything is contractible, like if arcs are contractible to points ordered so regions, then you can use this thing. Because if you have some, for example, this thing, so it will be contractible, so there's no change, there's no monodromy on it even, so you should just give only specify one thing on it. You don't need to specify everything. At any point you specify your shifts here, you specify your shifts here also, inside, you specify your shift on important parts, and that's all. Which corresponds to this picture, right? And these arrows are going from this to this, which makes sense if you think, because this contains this thing, if you see it here. So therefore there's arrow from this to this, but not from this to this, because it doesn't contain. So there's a restriction map. These are restriction maps of your shift. So this result is like that.
if you don't have this regular cell complex.
Right, so what you do, right? Then actually you never have this almost, because see the outside region, it's not contractible. So what you do, you just do this. You complete it. And you ask so you just put this thing, and then what?
Like you would find your.
Then you ask that your ship has no change in this direction, right? Actually, it should be constant. So you require these maps to be isomorphism. And here, this exercise isomorphism. So here, you put this, but you put everything in a simple way. You don't put any complicated map because there should not arise any fiber from this. But what this captures, it captures monodromy. How? If you can put A here, A here, A here, and A here. Okay, these are quasi-isomorphisms, right? These are quasi-isomorphisms. So you don't care about quasi. You can say that it's identity maybe. But here no, because see this quasi-isomorphism here? You can get rid of this. You can say that it's their identity because if you invert them, they will give you monodromy of A. So the reason that you make your complex cell, regular cell complex is capture monodromy. So that's the thing. And maybe finally I want to talk about some example and maybe I will just do so what to put, right? So how should we proceed if I want to find the subcategory? So this is equivalence, right? Here, this is equivalence. But what I claim is this thing is subcategory of this lambda, because which means this stratification enough to capture this lambda. So you don't need to have any other strata. For example, here this stratification code is all information, minimum information, to make this lambda realize. And so since this embeds in this, so this should embed somewhere, right? This should embed somewhere. So if I can find this, what is this? Which means that I describe this, right? So aim is to find this. So how can I find this? I hope I can find this category in 5 minutes. So what lambda condition? So we just talk about stratification. What lambda condition gives, which restrictions gives this lambda condition, right? So think about locally. So we are in shifts, we can think locally, right? So think about arcs. Local pictures. So think this we have an arc here. What does this arc mean in my local diagram? Which fiber does it say? It says that fiber's inward direction, right? Fiber's inward direction.
Downward.
Downward, yeah, that's not. It's always downward. It can be outward also because in the case of this. So it's downward direction, and we know since this is stratified, at least for starting point, we know we should assign this a chain complex here, a chain complex above W, and chain complex below U, let's say. And there is map like this, okay? So this is the stratification picture about this lambda condition. Should say something about this condition. So remember our local constant sheaf example. What does it say? So that can be generalized, right? It says that if your sheaf is so remember in that example we had remember we had a closed set, and here our sheaf is defined on boundary and the inside, right? And when it's in the boundary and inside, the thing was inverse, and if there's nothing inside on the boundary, it was outward. So which means if this and this are like, let's say this is W and this is U, and this this is U, which means it's inward. It means it's inward, right? If it's W, it's outward. Do you agree with this? This is our open and close example, if you remember. So what we require is this and this, these are quasi-isomorphism, then it means that my singular support will be downward. Okay, that's the condition for arcs. So first I build this thing, and then I ask first, if you see an arc, you think that you draw below, downward, it should be quasi-isomorphism, so that you can get the invert singular support. So this is first case. Second case is cusp. So what about cusp? So cusp, if you see locally, what should we assign for cusp? There's a point, there's arcs, and there's two regions, right? So it should be A, B, C, D, E. Am I correct? I put A for point, E for arc, C. So there are these maps, these maps, these maps.
C to D.
And C, C is outside.
Flip the arrow for C.
Sorry. So is there a map there?
Yes.
Right. It's correct, right?
Yeah.
So this is certification picture. What if I impose that the single support is in this direction? Here, so it's a local picture, but let's go even locally here. This is arc, so what we know is this should be quasi-isomorphism. Which one? This is quasi-isomorphism, right? Because this is arc and this is the below region. Also, same thing here. So this is arc and this is below region. Which is outside, so this is quasi-isomorphism. That's okay? So, with same region, with same logic, we can show that since this is bounded by this is also quasi-isomorphism. So I will simplify the picture like this. I will just say A, and B, so, okay? A, B. I will assume that they are identity. B, identity. This is triangles coming, so this is also identity. There's this B. Yeah, you get this kind of picture if you work out. Can I hear one more minute, Sophia? But if I say one, it means because there's the last case which is crossing. So this cusp condition introduced that if a point bounds this arc, then the map from going from point to arc is
Actually,
quasi.
sorry, before you do that.
Huh?
I see it. There are maps from A to B and J. Okay, sorry.
Uh-huh.
Yeah.
So by now we get this condition. If you see a downward map, it is quasi-isomorphism. This 1 and 2 says this. If you say downward map, so you should have only upward maps, which can be not quasi-isomorphism. But this last condition can introduce something different because let's say we have this crossing and downward. So you should put A letters, right? But we know already that if it's bounded by something, then it should be same. So if you start with south here, let's say south, this should be also south, right? The opposite that associated here is south. This also south because bounded, and this point also should be south. Here, no, there is no this upward map. This can be west, then this is east. But this is bounded by this, so this is also west. This is east, and this is north. So you will get this kind of picture. But what about here? So what will happen here? So that you need to first this condition. If you put all of this condition, they will say that your singular support lives in this region. Okay, with this condition, our singular support lives in this. But we don't want all directions here, right? We only want this direction. Remember, this crossing means this direction and this direction, not the between. So which means that if I take an arrow in this direction, there should be quasi-isomorphism. I don't want this arrow in my set, single support. So I should just analyze this arrow, if there's a change or not. So how can I do it? Again, see, I take a neighborhood and I take a point P. How can I find single support? I just need to look back and now. Like back part is this. And whole part is everything. So what is back part? This is west, east, north, east, this thing. But this is not single thing. This is shift. So there is this W set, E set which intersect on N. I need to glue this. I need to glue this thing. So if you glue this thing, so let's say the whole thing is up. So our shift will give this thing on up. So it's since I'm gluing these things, FW and FE with restriction to N, right? I'm going to so when you glue, you take limit, and limit in our case is kind of cone, which is shifted by -1. Okay, this is the thing. So I should compare this thing, this U with whole thing. Whole thing is south, right? So because this point means this whole thing is south. So I should see the restriction from south to FU. But to measure that it is quasi-isomorphism, you can take its cone, and if its cone is acyclic, then it means that it's isomorphism. So take cone of this thing, this map. But what is FU? FU is again cone of this thing. And if you work with this situation, if you understand this situation better, you get actual total complex of this thing. And you ask this to be acyclic. If it's acyclic, then you have no direction in this way, and your single support will stay in this, and you are done. So in there, if I can sum up, so this, you draw this picture, you ignore downward maps, you say they are quasi-isomorphism. Also, you have this acyclicity condition. So if you see a crossing in this part, the opposite, the chain complexes that you associate here they will give a square, and this square should, when you take a total complex of it, which means you take complexes, diagonals, etc., that should be acyclic. If you do this, then you will find. Okay. Oh. I'm sorry. Okay. Thank you.
Alright, any questions? Okay, then.
I don't know, breaking some laws. Should we maybe do the not with the Meister one, just to limit it?
But maybe I can do it for you, but I don't know if people interest as well. Okay.
Yeah.
Like. You mean this? You. And
Hold on that.
this one.
Yeah.
Okay. How can you work out this example? You say. Usually we care about the sheaves with zero outside. We just look for compact version of this category. So I will deal with this one. That's okay? It will take 1 minute. So here. So what should I do? I should put something here. We let's say. Or I can give you an object if you wish. So I will start with K. I will give K here. Okay? And 0 outside. And which means, okay, 0 here. I should give what here? 0, because here K, right? Here K, here K, here 0 because 0, here 0, here question mark. Here question mark, what same question mark? 0, 0. That's okay? So I get this, and I also this set is 1 and 2. Only thing I should check is condition 3. Yeah, which is acyclicity of this, which is impossible to do it because there are zeros here. So if I put, let's say, V here, if I put consequent this sequence, then this is not acyclic. But what I can do is this, I can change this 0 by k ident k. So I can put, okay, this k is k, this is k shifted by -1. Let's see this example, okay? This is also k ident k, of course. So let's see this crossing condition now. So I have k here, this set, k. Let's say it's complex, so it's 0k, let's say. And I have here k identity k. Let's say it's k identity k, same thing. So k identity k. And I have here, this is shifted by, it's actually 1. So I have this picture here. This triangle gives this picture. Do you agree? Maybe this k square, okay. Because we have this and we are summing this.
Can you do that again?
But can I, like,
Just do it. Just do it.
Don't
okay.
worry.
So let's see the crossing condition again, okay? So this, I put 0k here, and k0 here, k identity here, k identity here. Remember, this thing will carry to this place, which means actually this thing should satisfy acyclicity condition. What does it mean? I should sum up this. I will get k square, identity k square. Above I have k0, below I have 0k. I have maps from this to this. I can choose this identity, I can choose this identity because on homology this is 0, so I can choose this identity, this 0, 0. So see this map. So do you think it's acyclic? If I look,
Sorry, what does identity mean?
this
You don't
identity
actually
means this
mean-
identity.
No, that one is okay, but the
The
k
vertical.
squared and k squared.
This is identity to one component which makes it
Yes.
acyclic.
The other one is
That's
projection.
my way of working. I don't know which one. Now you think about this example, so what do you think? So here this K3 and this K3, right? And this hits one part of K, this hits other part of K, so this is cancelled. This is one part of K, and this only one K, this is also cancelled. So you have a cyclic system. Just homologic algebra example. Of course I didn't explain good, but
And just to make sure, you could replace the 0 with a k identity k because you're working in the derived category instead of
yeah,
working
that's
in
what the question in my mind was that, but you can change it. Why they're quasi, so they are quasi-determinate, but they are not same. So
in the category, in the derived category.
Can I say, so if, well, you have 6 entries, and then the second column, the arrow down there should really be 1, 1 instead of 1, 0.
what do you mean? Which one?
The second column, the second arrow going up, yeah, the one below, it should really be 1, 1 instead of 1, 0.
Is it 1, 1 or 1 minus 1?
It doesn't matter, but it can be 0. There's a reason for that. The coursing condition will impose, there are 4 regions, and then if you take the arrow across the line and take the cone of that, this cone will be preserved when you go across the crossing. And if that number is 0, and then the induced map between the cones will be 0, and that's not possible. So
Sure.
Yeah.
You mean this, right?
Yeah, they can be any 2 numbers, but both of them have to be non-invertible.
Sure. In this case, still it works, right? So. Okay. If you have not other questions, I'm done.